There's always
No,
relevance,
you
so
don't.
seek for the relevance for today.
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make
See the
yourselves
garb with all
comfortable.
the fringes on
Okay.
it? His garb?
See? People get it.
Yeah. Okay. So we should move. So has anyone got what we're talking about yet today? I guess we haven't really introduced it. We've talked about Bernoulli for the last little while, and even though it's implicit in what we've done, we haven't really stated it, and that is that everything that we do is relative. So the control volumes that we've taken, and also the frame of reference, I guess, mainly, is a relative statement. We've talked about moving up and down in an elevator and experiencing acceleration maybe as we go up and down in an elevator. Obviously, elevators mainly go at a constant velocity, but at least when they start up, they accelerate. So if you imagine an elevator that accelerates or goes at constant velocity, then it matters whether you're on the elevator and looking at what happens to water there, or if you're standing off the elevator and watching the elevator, one of these glass paneled elevators in Hyatt's, go up inside the hotel, and you'd have a different frame of reference if you're standing next to the thing as you're going up versus being at ground level and watching the elevator go up past you. And so that's kind of important in the things that we'll do now. We'll talk about conservation laws, and it's important for us to be able to understand at least a little bit about frames of reference. So the relevance of the fireboat, of course, is that if you're in front of the fireboat and you're squirting water forwards at 1 meter a second, then relative to you, that's traveling at 1 meter a second. If the boat is also moving at 1 meter per second and squirting out at 1 meter per second, then clearly the water that's coming out of there to a static observer is going at 2 meters a second, even though to an observer on the deck it's only 1. And so we need to be able to make that distinction to be able to understand something about how we calculate accelerations. Because changes in velocity, which control this ma term in F equals ma, which we've used in Bernoulli, which controls this v squared over 2g term, have to be relative to some reference frame. And so it matters what that is. And we've kind of already done this, but we haven't really dealt with it in a formal way. We haven't really said anything about it. So that's what we'll do today. We'll talk a bit about reference frames as we get into this. The other example which we'll ultimately use, or another example much closer maybe to some of your disciplines, are things like wireline operations. So that's nice music. And so for those of you working, actually all of the areas, all of the engineering disciplines that are represented here, petroleum for sure, environmental systems, environmental geophysics and borehole geophysics is certainly used in that as well. Maybe energy engineers, and certainly in mining, prospecting for new finds, borehole geophysics is used quite routinely. And the basic idea is you have a drill hole in the ground. Typically in petroleum you've drilled it without any kind of record of anything except for the cuttings that come back up the hole. You don't have core from the hole. And you'd really like to know what the architecture of the subsurface is in terms of the reservoir which is present at depth. And you have basically no information on that except a few pieces of chips of rock that come up that might typically be much, much smaller than the tip of your fingernail, small fingernail. And so one way to do that is to drill the hole quickly with a tricone bit or whatever it is in a rotary hole. Don't take any core, although you can take core, but it's very expensive and it slows things down. And then after the hole is completed, you run geophysics down it. And so you take a sonde, and the sonde has some kind of sensor in it, and you just drop it down the hole and then bring it up the hole. And so typical sensors that you might use, so here they're just putting the sonde in an enclosure. They've got a blowout preventer to keep pressure in the well on top of the well. they're mating the two together with it closed at this location. You saw these two things closed laterally. You put it on, you open up those valves. So if you opened up the holder of the wireline tool, the son to the pressure, and you just drop it down the well. It's called wireline for obvious reasons, because it goes down on a wire. And you drop it down the well to the bottom, and you bring it back up, and you measure something. I guess this is in Canada, because the guy's got half a Canadian maple leaf on his back, and also the snow on the ground. Of course, you know it's all snow on the ground in Canada. And you measure something. So the things you measure, you might measure natural gamma ray emissions from the rock, which are typically radioactive elements are locked in shales and clay layers. And so those tend to be high in gamma counts, so you can identify where shale layers are. You might have a caliper log that measures the width of the hole, and so that measures places where it's collapsed, and you can make some inferences about that. You may use a spinner log, which is related to this class, which is a little impeller that goes down the hole, and you run it down with the impeller going to measure the relative velocity of that impeller as it goes either against static fluid or flowing fluid. You pull it back up, you measure the change in the impeller velocity, and you make some measurements of the flow rate in the hole. And so that's useful because if you have fluid going into the hole in one place, traveling along the hole, and then going out of the hole in another place, you have some way of being able to log that as maybe permeable layers, which might be useful parts of your aquifer or reservoir to be able to accommodate. I guess I have this. Do I have the same one twice? One of these I had. Yeah, so I'm not sure whether you see this any better just from a... No, I guess I don't want to do that. Okay, stop that. And so, so some of the things that we'll look at today, obviously those have a change in frame of reference. As you go down along the hole, it's obviously moving in space. And so we'd like to be able to use that information in some way to be able to correct. So we'll use that as an example today once we're doing. So the relevance of all those little videos were to make the case that frames of reference are kind of important for us. We've implicitly assumed this in some of the things that we've done. For instance, when we look at what we've done so far in terms of Bernoulli's equation, we've taken a frame of reference which actually moves along the streamline. We haven't really said that explicitly, but you'll remember, if we recall what goes on here, we have, this is written poorly, but we've basically taken F equals ma. We know which parts are which. Forces and accelerations are vectoral quantities. They have direction as well as magnitude. For Bernoulli, it's a scalar relationship. This is a streamline velocity, and so we've actually taken these along the streamline. So the force along the streamline and the acceleration along the streamline is de facto what we've taken. And what we've done, for instance, in looking at this, is we've taken this as a mass and a rate of change of velocity with time. And so we've done this, and we've converted it, if you remember, to a mass times a rate of change of velocity, again along the streamline. How it changes with time. But we've also done this. We've multiplied by 1. And so this now, again, what's the change of location with time? It's just the velocity along the streamline. And this is a rate of change of velocity along that streamline. So this is actually now, we've converted from something that is defined exclusively in terms of time, a rate of change of velocity with time, if you're attached to the particle of fluid, to something that we can also think as, and we'll call this term convective acceleration. ACCN is short for acceleration. And so now, instead of something that relates to how something changes in time, it's how something changes, a velocity changes in space as we go from A to B downstream, and as a function of an average velocity that it might be traveling at in the first place. And so that's now we're able to say something now. If we take the Hyatt elevator with the glass case in it, either we can be attached to the elevator to see what the water experiences as we hold it as it goes up, the rate of change of velocity with time of that packet as we stand next to it, or we can be a bystander that stands in the lobby and watches it go up past us and see how the velocity of that changes as a function of location, not time. And so that's basically what we're trying to do. And so what we could have done is we could have written this expression in terms of the so-called material derivative or the substantial derivative. And so the substantial derivative, you've seen it in your other classes, is uppercase D, V, D, this is a T, even if it gets obscured by the line. And that allows us to be able to accommodate both ways of looking at it. Whether we're attached to it going up in the elevator, or whether we're standing back from a different reference frame looking at it going up in the elevator. And that's really what we'd like to talk about today. And of course, we did that and we didn't really talk about it, but we now have a chance to talk about it today. I won't recap our stuff on Bernoulli because we spent some time, but remember, this is the MA term, and these are the two F terms on either side. Not this and this, right? I could have written it, should have written it V squared first, and then it would have been already parsed out that way. So that's kind of the important things that we'll talk about today. So we're going to start talking for the next 3 weeks about conservation laws. The first one we'll deal with is conservation of mass. The second one we'll deal with is conservation of momentum, which is F equals ma, really. And the third one is we'll talk about conservation of energy in terms of how how engines provide work. And so to be able to do that, the first step we need to do is talk about reference frames. So that's our today's purpose. It turns out that we've already talked about them in some respects. If you think about what we've done already, remember we talked about Bernoulli both along a streamline and normal to a streamline. Mainly we spent time talking about along a streamline. We've said that that satisfies this F equals ma. And so that's really conserving. We're conserving energy in a little differential cube that we then extend along a streamline. And so actually what we are doing is we've not really stated it explicitly. We've done it for the mass change, but if we draw a couple of streamlines between points 1 and 2 and look at the flows into and out of those, V1 in and V2 out, we've actually conserved momentum. So what Bernoulli does is conserve momentum. Bernoulli conserves momentum. Although we haven't stated it. That was basically the expression we worked from to derive Bernoulli's equation. It was this. This is that statement. Conserves momentum. It says that if momentum is destroyed, there's some kind of force that's applied. You know it. I take a ball or something and throw it at the wall. The ball is happily moving at some velocity, hits the wall, it changes velocity and direction, it transfers that momentum to the wall and then back to the ball as it comes back. So Bernoulli implicitly has done that. We haven't explicitly stated it, but the other expression that we use to be able to tie this together, remember, if we have only 4 knowns in our 6 unknowns for Bernoulli, upstream and downstream, then we've tied that together by trying to associate 2 of the velocities to each other by so-called continuity. And so continuity also, or our conservation of mass equation, is actually not so dissimilar. Again, we'll draw it between 2 streamlines, between points 1 and points 2 on each of those streamlines. I guess that was the same here, and equivalent points on the other streamlines. And we have some velocity out of here, and we have some area here. Then we've rationalized that by the fact that when we look at this, since this, by definition, a streamline is a path that a particle travels along, and therefore cannot, by definition, go across, then these are just impermeable walls to our container that it travels along. And so if you want to put this in verbal terms, it says mass rate in equals mass rate out plus accumulation. And so we could actually, well, it might be worthwhile writing that. So what does this say? So V1 A1 is equal to V2 A2. We could also rewrite this as mass rate in minus mass rate out equals mass accumulation rate. And so mass rate in this case, mass rate in would be a velocity times an area times a density. Velocity times area is meters cubed over time. Meters cubed per time over kilograms per meters cubed is kilograms. So it's kilograms per second would be the units of this. The mass rate out would be velocity out times the area out times the density out. We don't want to change. And this equals accumulation. So in other words, if more stuff goes in than leaves, then by definition it has to accumulate. So if 10 people go in 10 minutes and 9 people go out in 10 minutes, then you've accumulated 1 person. And so the difference between those is just that simple balance. You can do it in differentials, or you can do it by discrete particles or discrete people, bodies if you like, but it's the same thing. And so really the first things that we'll talk about conservation of mass. We already have a statement kind of for that, which is this. We'll talk about conservation of momentum. Bernoulli has been our simplified case of dealing with that for the cases that we're interested in working with, and we've got that, but we'd like to be able to use it on much more complex shapes than that. And we'd like to be able to apply it for conservation of energy. And of course, Bernoulli, as we have it, as we've talked about it, has been purely in terms of upstream conditions, downstream conditions, and the other conditions that allow us to be able to deal with these other components are these things we haven't talked about yet. How much energy we put into the system, and how much energy we expend in our system by going through joints and bends in the pipeline system, and also in frictional losses as we spend fluid along the pipeline. We said that Bernoulli is for incompressible fluids and inviscid fluids, most importantly inviscid fluids, so they don't lose any energy in moving around. So the same, the analogy you've taken this, move it here, takes energy. If I want to move it back to its starting point, I have to expend double the energy to get it back. And so it's energy that's expended that doesn't come back. And so in reality, we've kind of broached on all of these 3 conservation systems in what we've done. Continuity, mass rate in equals mass rate out. Mass rate in minus mass rate out equals accumulation. We've talked about energy in terms of Bernoulli, and we've talked about we've talked about momentum in terms of Bernoulli, and we've talked about energy in terms of Bernoulli in the terms that we haven't yet figured out exactly how quite to quantify these. We'll figure that out. Okay. So yeah, go ahead.
Isn't the second area supposed to be area 2?
Probably. Yeah. It is indeed. Thank you. All right. So what we'll talk about then in this is control volumes. We'll spend most of the time talking today about static and moving reference frames, and we probably won't talk about Reynolds transport theorem. But Reynolds transport theorem is just a generalization that allows us to be able to look at doing this calculation for the balances of energy into and out of a system, or momentum into and out of a system. No. So the 3 things we'll talk about when we talk about after we use reference frames will be conservation of, first of all, mass. Secondly, momentum. I'll just, by cameo, I'll put our simplified views of what these are. Momentum would be F equals This is Newton's second law, right? Mass remains constant. Rate of change of velocity is acceleration, so it's just another way of writing Newton's law. And finally, energy. These are both kind of Bernoulli-esque. ESQUE, for those of you who have a bit of French flavor in you. They look like Bernoulli. That's the extended Bernoulli equation that just has all these components, which we'll deal with in due term. In turn. What other things should I say? Yeah, okay. So let's look, and any other questions? So let's look quick at control volumes. I won't go through this. So this is the basic idea. When we are talking about control volumes, you could imagine a number of them, and they're kind of highlighted by these schematics. So static is what? Static is a pipe. You have water flowing through it from one side to the other. You define an upstream portion, a downstream portion, and you can look at the rates in and rates out, and you can figure out whether stuff accumulates or not. So static is a pipe that you can cut at any point you like, and you can just do the mass balance of what goes in and what's out. It doesn't move in space, doesn't deform because it stays the same size. A moving control volume is one that is not changing in volume, but is changing in space. So the jet engine, which is what I've tried to draw on the second one down, is a good example of that. If you're sitting in a plane, looking at it on the wing, then it's always attached to you, and it's always moving in the same place. So it's static and non-deforming. But if you're watching the plane go past you, then physically it's moving, but not changing in volume. And the third one in the three possible combinations is one that's both moving and deforming. So the example of that would be a whoopee cushion or a balloon that you blow up and you just let go through the air, it zips through the air. It moves relative to you because you're static and it's going all over the place in apparently random directions. But it's also changing volume as it kicks out the volume of air inside it under pressure to release that pressure to the atmosphere, which is at a lower pressure. And so those are the three control volumes that we'll look at. So we'd like to have some kind of formalism so that we can now look at both these static control volumes and moving control volumes. And actually the fact that they deform is also merely a consequence of the fact that different surfaces on the surface of that whoopee cushion or the balloon are moving at different rates relative to each other. So that's just a relative velocity thing as well. It's deforming, but the sides of the balloon are changing are moving relative. If it's getting smaller and you attach yourself to the front, then the front is moving at some velocity. I guess the back is moving at some faster velocity because it's getting smaller and it's getting closer to the front as it contracts. And so it's just a relative velocity also. And so I won't use any of the things we've got here. I'll use my own stuff. So we're going to go through this it's an important concept, so let's spend some time doing it. So the best example I can think of to do this is the idea of a wire line, which is why we introduced that first. So we are happily in the 6th week. We're really talking about conservation of mass, but really we're looking at frames of reference. And our desire is to be able to, if you like, understand this material derivative, the substantial derivative dv dt, or actually change in anything as a function of time. So the so-called substantial derivative or material derivative. So the best example I can think of for this is basically a wire line. So what you would typically have with a wire line, and it's easier, you could think about this as temperature, or you could think of this as maybe fluid pressure if you lowered a pressure transducer down the borehole. And that is that if you look at going down from the surface of the Earth in our coordinate system, using our coordinate system, x, y, z upwards. So z downwards is negative z. Typically, if you look at the surface of the Earth and you measure temperatures as you go down, they go down at some gradient, thermal gradient. Thermal gradient is typically, a high gradient would be 50 degrees centigrade per kilometer, and a low gradient, a regular gradient here might be 25 degrees C per kilometer. So that's the gradient as we go down. So if we want to write that slightly more mathematically, this is a change in temperature as a function of depth. And so this is change in temperature with depth. Not time. This is my z's with a bar through them. In this particular case, this is a temperature change with depth. This is positive temperature change. This is negative depth. And so actually, although we always think of these as everyone will say 25 degrees centigrade per kilometer, if your reference frame is so that positive depth is upwards, then you have to have a minus in front of this to be able to make this the correct sign notation. Okay? And so what we're going to do is we are going to drop a sonde down here, and this sonde is going to go at some velocity downwards. And so what we'd like to be able to do is understand what the temperature changes from measurements we make on this sonde in some uniform way. So not obviously, also since positive z is up here, this would be a negative velocity, right? Because you're going downwards. And say we go down at a magnitude of 1 kilometer per hour. Let's make our one diversion away from SI units. We'll use hours instead of seconds. And it's going to be, from what we just said, this is going to be negative, right, by definition. And so what we'd like to do is we'd like to be able to say something about how temperature changes with time as we go down. And so this temperature here is attached to the sonde. S-O-N-D-E. And this is how we'd experience the temperature change. But what we can do is, in exactly the same way as we've done this before, we could write this out as a rate of change of temperature as a function of time, plus a rate of change of temperature as a function of time, plus a rate of change of temperature as a function of time, plus some others. We can only do 4 total. Actually, why don't I do all 4, just because these are the only 4 we can have. And the reason I can say we can only have 4 is because we have a 4-dimensional world. Our world is x, y, z, positions in this room, and also time, how that changes with time. And so in the first one, and the reason I can say that uniquely defines behavior is because they're all orthogonal to each other. Distances in the x and the y and the z directions are all orthogonal to each other, so they have no relative component that affects the other. And time is also separate from that as well. And so that's why I say that we can only use 4 of these. So this one, I might like to put in time, but I'm not going to bother doing that because it just makes it messy, because that's just 1 and we just don't need to do that. This one, I'm going to go as a function of x, since we've done this. This one is behavior in y. And this one is in z. So I'm just multiplying each of them by 1, but really what I'm trying to do is figure out how I can take the components of these behaviors as they change in x, y, or z and use that in some useful way. In this particular way, x, y, and z is like this. So z is vertically downwards in this direction. The sonde's only going in this direction, and as you go in x or y, the temperatures don't change. And so I'm just going to ignore these in this particular case. So in this particular case, the change in temperature in X or Y isn't going to change, and so I can get rid of these. In other words, if I go 50 meters from here and look at going down in the Earth, the profile with vertical depth will be exactly the same in terms of temperature. And so if I go horizontally between those places, at any particular depth that I choose, there'll be no gradient, no change in temperature with X or no change in temperature Y. And so now what I've done is I've changed it into something which is a reference frame. So this now is what? This is velocity in the z direction, not the streamline direction. And so if we wanted to, then I can just write this as rate of change of temperature with time, and the only term that survives is the velocity in the z direction. I'll just write this backwards, with the rate of change of temperature with elevation. So this is, we've said, is attached to the sonde. This is fixed in space. So if you like, this is from an observer. If I can draw it, this is supposed to be an eyeball. This is how people draw these things. This is if I'm looking at this particular distribution of temperature with depth. Not traveling in space, not going up or down, but looking at it in space. And so now, what I'd like to be able to do is I can tell, you can now tell me, if I was attached to the sonde and moving down with it, how the temperature I would experience would change as a function of time. So what is it? How does temperature change in time in this fixed space? Well, it looks like this right now. It looks like this tomorrow. It looks like this 100 years from now. This term is going to be equal to 0 because it's not changing in time. It's fixed. The sonde is going down at 1 kilometer an hour, minus 1 kilometer per hour. And this temperature change with depth is this geothermal gradient. It's equal to this is equal to minus 25 degrees C per kilometer. So if you multiply these out, then if you're going down in this sonde, the temperature change the rate of temperature change you experience is minus 1 kilometer an hour times 25 degrees centigrade per kilometer, which is 2 minuses make a plus, right? And it's so. And we didn't have to use calculus to be able to figure that out, right? You could figure that out just from knowing what we're doing. But it's an absolutely rigorous way of being able to do it, to be able to figure out exactly how to calculate how things change. We've chosen to do it with a scalar. Temperature is a scalar, pressure is a scalar, same magnitude in all directions, but we can also apply it to vectors as well, which we will do. Let's do one other thing as well. Say, for some reason, we were getting, well, why is there a geothermal gradient? Anyone know? Used to be thought, I guess, in Kelvin used to think, Kelvin of Kelvin units, thought that it was because the Earth was cooling down from being created primordially, and he calculated the age of the Earth as a few thousand years old. So in other words, created from a blob of matter in the universe, conglomerates, it starts off hot and it cools down because the exterior boundary condition is cold and heat diffuses out. And that was the prevailing view in Kelvin's time. Then Rutherford, the guy who first split the atom, had to apparently give a talk with Kelvin in the audience, and he had a different explanation. So his explanation was, we have a geothermal gradient because of radioactive decay in the center of the Earth or throughout the Earth. That generates heat, and that heat seeps out to the outside, and so it creates this geothermal gradient, which is roughly constant, doesn't really change with time. So it's not cooling down with time, and we measure it now, but it's roughly constant because it's a constant rate of generating heat from radioactive decay. And apparently he was giving this presentation when Kelvin was there. He was a young researcher. He was worried about this esteemed guy in the audience who actually fell asleep and didn't hear his explanation, but it was fine. So ultimately, Rutherford wins the day, I think, in terms of current acceptance. So imagine if we have radioactive decay and we turn it on. So in other words, after 1 hour, the temperature looks like this. After 2 hours, it looks like this. After 3 hours, it looks like this. So in other words, let's assume that this changes in some magnitude from T0 at the surface to alpha times time. So alpha is a rate. So what would alpha be? Say alpha is equal to 5 degrees C per hour. So in other words, this whole thing is heating up. So if we went down 1 kilometer and we start off when this is 0, we know we've gone down 25 degrees centigrade. So this would be 25 degrees centigrade. But we also know in the time it's taken us to get there, it's also gone up another 5 degrees centigrade because this is 1 hour and this is 5 degrees C, right? That's the delta T due to this extra component. So now, how do we use this expression to do that? We want to calculate the change in time, temperature with time. We're going to use exactly the same expression as before. It's going to be equal to the static change in temperature with time plus the convective portion, as we've called it. So what's going to change? Well, rate of change of temperature with depth hasn't changed, right? All of these lines are parallel to each other. So this is still minus 25 degrees centigrade per kilometer. We're still moving it down at minus 1 kilometer per hour. But what is this? We have the temperature is equal to alpha times T. Take the derivative of this, what do we get? Take the derivative, we lose this. So if we take d dt of T plus alpha T, we end up with alpha. Alpha is equal to plus 5 degrees centigrade per hour. And so, as a result of this, we'd end up with this overall term being plus 30 degrees centigrade per hour. And so it says exactly what we've known, right? We go down a kilometer, takes us an hour to get there. The temperature's gone from this magnitude to another 5. This was 25, and this now should be 25 plus 5, which is 30. That's all. That's all material derivatives are. So the takeaway point is that this is the temperature change that you physically experience as you go down in the sand. You're moving in space, and you're seeing what happens to this, to the temperature outside the elevator. But you can get it by being an external observer and looking at the system and seeing how quickly that observer is moving down across the scene, if you like, and being able to know something about how temperatures change within that scene. And that's all that substantial derivatives are. And so that's what we'll use. So it's useful to be able to do that. We've already used it, as we made the point before, because what we've done is we've never written it this way, but we have basically F equals D we've basically been working with this, and so mass doesn't typically change as we move around, but for instance velocity does. And so our reason for doing this is that now we can say something about this behavior. Our first entree into it has been with this relatively straightforward system, which is due to the fact that we chose a scalar, right? Temperature has a magnitude but no direction. When we start looking at F equals ma, we know that force has forces in x, y, and z, so there are 3 components, and also there are components of velocity in each of those directions as well. So we have to deal with that. And so what we could also do is we can now take it to look at vectoral quantities. So let's just quickly do that. So let's look at vectors. And, well, let's just take exactly what we had before. So, yeah. So we realized that this term F would be a force in the x direction, a force in the y direction, and a force in the z direction. Don't mean to make you turn your pages back, but that's what this term is. And so let's make life easy for us by just taking one of those. And so if we take just resolving forces in the x direction, we can have the forces in the x direction are equal to mass times velocity in the x direction dt. And if we write that out, we can write it out as force in the x direction is equal to, I'm just going to write it again, velocity in the x direction dt. And we're going to do exactly the same as we did before. We're going to take mass outside the bracket because it will apply to all the components. And we're going to write it as a rate of change of velocity in the x direction with time plus a rate of change of the velocity in the x direction with time. It's going to get a bit repetitive. There's going to be 4 total for our 4-dimensional world. These are my t's, by the way, they're not z's. And velocity in the x direction as a function of time. We're going to do exactly the same as we did before. We could put time here, but I'm not going to do it. Or sorry, rate of change of time, dt and dt, but I don't want to do that, so just because it clouds things, so I'm going to remove that. And what are the other ones? This is a rate of change in the x direction. This is a rate of change in the y direction. And this is a rate of change in the z direction. Bless you. And so now this is velocity vz. This is velocity vy. This is velocity vx. And so if we wanted to write this out in longhand, again keeping the brackets with the m outside, this is rate of change of velocity in the x direction with time plus velocity in the x direction times the change in velocity in space in the x direction plus velocity in the y direction times the change in velocity in the x direction in the y direction plus, whoops, the velocity in the z direction multiplied by the rate of change of velocity in the x direction in the z direction. So, looks a bit complicated, but we just have to keep account of all our indices.
Question?
Yeah.
Would those automatically be 0 if we already accounted the velocities already going in the x direction? Why would it also go?
Only for the case that we've talked about. So they could be, if you had a velocity in the x direction and it happened to change as you went in the z direction, then this would be finite. So only for our in this example, we threw those away. Can't always do it. So this is the general thing. And this is called a substantial derivative, and it's written in a variety of different ways. And so that's useful for us to remember because now we can also calculate accelerations in using either reference frames. So we basically have this substantial derivative defined. And so now we can either measure the accelerations we have as we move up in the elevator from ourselves, as we hold the piece of fluid or the ball or whatever it is that's moving through the system. Or we can stand back and view it from a distance and be able to figure what these things are just by looking at it. And so to cement that, maybe, let's just quickly go back to our notes if people don't have questions. So we've avoided a whole bunch of derivations that we don't need to deal with, don't need that. You can go back to this. And we've basically come up with, this is where we are. This is what the book uses in terms of terminology. This is the acceleration term. This is our term dv dt. This is acceleration, rate of change of velocity with time. It's a vector, as it has velocities in x, y, and z, x, y, and z, x, y, and z, and x, y, and z. And you go through this. And so what we've done is we've basically derived this first expression here, the term in the x direction. And if we look at accelerations not only in the x direction, but in the y direction, then we have 3 other components, which are the 3 terms which are these. So I think it's something that you perhaps need to just go and digest at your own leisure. It's much more complicated when we have vectoral quantities because we have this quantity is a vector and we end up with this three-dimensional component, three components, we end up with three terms. If this component is a scalar, as it was when we dealt just with temperature, then it's at least a little bit simpler. We just have one equation. And so then we can use that to be able to calculate accelerations in any of these relative frames. It may seem kind of esoteric that we want to do that, but it's quite straightforward. But we do need to do it. And I guess the proof of the pudding that we do need to do it is that we've already done it. When we used the equation for the static pressures in a fluid that's accelerating in a bucket, we used that expression to be able to derive Bernoulli's equation basically along a streamline. So we basically did this without saying anything, making a big deal about it. And so if you have a velocity at point 1 and a velocity at point 2, if they're different in going from along the streamline, then by definition there's been an acceleration. Not because of the fact it's changed direction in that particular case, because we take it along the streamline, so they all have the same direction even though it bends, but because it's going at a different physical speed. And so we can do that by this convective term that the velocity has changed as you go in direction. So a very simple way, very simple example to do this. So let's take a flow field. And if we look at this flow field in x and y, let's assume that we could define this flow field. I think this example is taken straight out of the book. So the flow field is that we give it a certain expression. So in other words, at this point here, the velocities in x, y, and let's forget z because it's out of the page. It would be towards me. It's being in my face, right? Because of the coordinate system, x, y, and z. Then the coordinates of this point are 0, 0, 0. And so the velocity at this point in x, y, and z would be 0 in all directions. If we go to a point which is 1 here and maybe 1 here, then what are the velocities? X is 1, so the velocity in the x direction here is 2 times 1 equals 2. The velocity in y, well, y is equal to 1, so the velocity in y is equal to minus 1. And the velocity in z is equal to what? It's equal, well, I guess if z is in the plane of this, then z is equal to 0. And therefore, the velocity in z is also equal to 0. So if we just take this plane and looked at making a contour map of the different velocities in x, y, and z, we'd need 3 contour maps, of course, right? Because it's 3 quantities. We could say exactly what that is just by looking at that. And so what we could do also is we could use these velocities. So this is what we've called Vx. This is what we've called Vy. And this is what we've called Vz. The book uses this terminology. We could use this to calculate what the acceleration field was as a function of that. They're not changing with time. So there's no change with time, so we get rid of this. We definitely have velocities in x, y, and z. So these terms are finite. But what about the derivatives of these? The change in velocity in the x direction with x, well, that's going to be finite, right? du dx is just equal to d dx of u, which is just equal to 2x, which is equal to 2. We lose the x, right? dv dy is just going to be equal to minus 1. And dvz dz, which is this one, is just going to be derivative of this, which is also going to be plus 1. This is minus because of this term. This is positive because of this term. So that's it. If you look at any of the other ones, for instance, if you look at these, the change in velocity in the x direction with z, change in velocity in the x direction with z, so take the derivative with this respect to z, is just 0, right? So all the other terms work out to be 0. And so now, if you put the numbers into here, u1 is equal to 2x. The change in velocity in x with x is equal to 2. So it's times 2. Because each of these terms here are 0, they don't register. The next term would be the velocity in the y direction, which is, this is minus y here. dvy dy we did down here, which is minus 1. So this whole term, if you like, should just be equal to minus y times minus 1, bless you, which is equal to plus y. Likewise for this, the other term that exists here. And so you have the result down here all worked out. And so basically it says that we don't know, and we're not traveling with these particles of fluid through the system, so we're not getting our acceleration from moving around with them in any useful way like that, but we're standing statically and seeing how the velocity changes as we go from one point to another. And if we do that, we can use these terms here, which is really all they're doing. And the terms that we get out of it is that the acceleration of the fluid in the x direction at any point is equal to this. If you choose x equals 0, then the acceleration is 0. If you choose x equals 1, the acceleration is equal to 4, plus 4, etc. The acceleration in the y direction, again, at any point is equal to plus y. And the acceleration in the z direction is equal to plus c. And so that allows us to be able to say how the fluid pressures, how the fluid velocity is changing. If you want to write this out in this vectoral sense, then the other way to write it in the book is to also multiply, this is 4x, which is this. This is plus y, which is this. And this is plus z, which is this. These other terms, not of course, but these other terms are just the directional vectors. So I is equal to a unit vector in the x direction. So in other words, a unit length vector in this direction just multiplies it to be able to give it direction. So this, we're thinking of this as a scalar value of acceleration, but it's not a scalar, right? It has direction, a magnitude, and also direction. And so this is in the x direction. What's the vector in the y direction? It's going to be 0, 1, 0. And the unit vector in the z direction, you've probably already written it down. So I, j, and k are just the unit directions. I, j, k in these directions. And so that's the flow field. And so from not being attached to the particle, we've stayed statically. And by looking at how velocities change in space, these so-called convective accelerations, change in velocity of the space, just a fancy word for convective accelerations, we've been able to say something about what the local acceleration is.